Alrighty guys, today we're going to be talking about solving exponential equations and talking about exponential word problems. So the key to knowing you have an exponential equation is that you have a variable in the exponent, okay? And you are trying to solve for that variable that is in the exponent. So it's trapped there. So we need to be creative in order to get that variable out of the exponent so that we can solve for it. So there are going to be two ways to solve these exponential functions. The first way is to make the same bases, right? Make like bases. Okay, this really only works if you have numbers on opposite sides that are powers of one another. For instance, 2 and 4, right? 4 can be rewritten as 2 squared, so they can be both written with the base of 2. 3 and 27, or actually let's try 9 and 27, right? Both can be rewritten as base 3, right? 3 squared is 9, 3 cubed is 27. So we would use this method for those types of equations. Now, if you can't make like bases, what you are going to have to do is you're going to have to use logs. Okay, how do we use logs? Well, just like we solve log equations by rewriting things as exponential expressions, we're going to be doing the reverse. So we're going to have to write your equation as a log. So if you remember, log, anytime we're working with a log, base b of a equal to x, that comes from b to the x equal to a. So we're just going, instead of working this way, we are going to be working that way. So taking a look at this example, this one can actually be done in both methods. So I'm going to show you both methods. So like bases will be done in the following way. Okay, 16 is 2 to the 4th. Now, having a 16 in the denominator means that my exponent is going to be negative 4. Okay, so this right here is 1 over 2 to the 4th, which is equal to 2 to the negative 4th. So I can replace this with 2 to the negative 4, and it is still equal to 2 to the 2 plus x. So now they are written in the same basis. Anytime we have the same bases, we can essentially drop them because these two exponents have to be equivalent in order to make that same base equivalent. Okay, so I'll subtract 2 from both sides, and I get negative 6 is equal to x. Okay, now the benefit of having like bases is that it stops us from having to memorize the log equation, but again, not everything can be solved this way. Now, how do we solve this using logs? Well, if I take a look at the original, I can rewrite this as a log in the following way. Log of base, well, what is my base? 2, okay. Of, and it's always going to be of the answer, which in this case is 1/16, is going to be equal to my exponent, which is 2 plus x. All right, so now we have taken the x and we have removed it from the exponent. All that's left is isolating. Okay, so log base 2 of 1 over 16 minus 2 is equal to x. Now, if this log doesn't work out to a nice thing, that would be considered your exact value. Okay, but we already know that the answer is negative 6, so it should still work out to a negative 6. Now, just in case you forgot, in order to get the log with the blank box here and the blank box there, you have to press math, and you have to scroll all the way down to log base with the parentheses. Okay, so if you type that into your calculator, log base 2 of 1 over 16 minus 2, you get negative 6 is equal to x. So you do get the same thing. If you're not super comfortable with the like bases, logs are always a nice way to go for some of these questions. Okay. Solving exponential equations. So now here's another one slightly different. This one is different because my base with the exponent is not isolated. Okay, so in order to be able to write something as a log or to have like bases, we need things to be in its just the base with the exponent. So we're going to divide both sides by 2. And we get 5 to the 4x minus 1 is equal to 3 over 2. Okay, now if we look at this, we know that we will never get 3 over 2 to look like a 5 with no matter what exponent we use. So this is an equation where we have to use logs. So log, what is my base? What is the answer? Equal to my exponent. Okay, now all I have to do here is isolate my x by adding 1 and dividing by 4. Okay, now this would be what we would consider our exact value. Okay, you type that whole thing would be inputted directly into the delta math. Or if you want to find a decimal equivalent, you can type this into your calculator, okay? And then when you type this into your calculator, you want to make sure you read the directions of the question. If it says hundredth, 2 decimal places, thousandth, 3 decimal places, etc. So I'm just going to round this to 3 decimal places, and I get x is equal 0.313. Okay. Now remember, we can always check all of these equations using that y1, y2 trick where I type in this side of my equation to y1, this side of my equation to y2, and find their point of intersection. So you should be checking your answers using that system of equations trick that I taught you. Okay, so let's try this one. Now we have 2 things. Is my base isolated? It is not, so I need to do that first before I try anything else. So I subtract 3. I divide by this 3 now, and I get 10 to the x plus 1 is equal to 100. Now this one can actually be solved in either way, and I'm going to show you both just so we practice. With like bases, remember 100 is 10 squared. So I can replace, I can rewrite this side and replace 100 with 10 squared. And because they have like bases, I can just write the exponents equal to each other. And we get x is equal to 1. Now, if you didn't recognize this, you can also solve this with logs. Okay, so how do I solve this with logs? Well, it's a log base 10, which we know is the common log, so we don't actually have to write the 10, of 100 is equal to my exponent of x plus 1. I subtract 1 from both sides, and you're lucky. Remember the log key for the common log, right? Base 10 is right there on the front of the calculator, next to the 7 button. So you just type that log of 100, subtract 1, and you get the same 1 is equal to x. All right, so that works also. Again, we did it in 2 ways, so you should trust that this is the right answer, but you can also type this side into y1, this side into y2, and find the point of intersection to double check. Now, the only thing that might pop up sometimes, right, depending on your luck with delta math, is e as a base. Now, this is solved the exact same way, right? We are still isolating. We can still use logs, but instead of using log base button, we are going to use the ln button, which is the natural log. And again, that is found on the face of your calculator next to the 4 button. So first we start by isolating. So I'm going to add 8 to both sides. I get 5e to the 2z plus 4 is equal to 8. I divide by 5 on both sides. E to the 2z plus 4 is equal to 8/5. Now, again, we don't need log base. We can just use ln because that is the same as log base e of our answer is equal to my exponent. Okay, and all that's left is to subtract and divide. And 8 over 5 minus 4 and divide by 2. Again, this right here is my exact value. I would type this into my calculator to get an approximate answer of negative 1.765. Okay, and again, if you want to check this using your calculator, type this entire side into y1, this entire side into y2, which is just a 0. Find their point of intersection, and you should get the same value in the x. All right, now the last thing we need to talk about is word problems, okay? Modeling an exponential function and then using that to solve. So for this, I have a word problem. You buy a new computer for $2,100. The computer depreciated in value by 50% annually. When will the computer have a value of 600? Okay, so anytime we have this annual change or, a certain percentage, we're going to be using the equation y equals a times 1 plus or minus r to the t. Okay, where a is my initial value. If it's for interest questions, keeping this in mind for the future, this would be called our principal value. Okay, but it's the value you start with. R is my growth rate. Okay, and that would be plus if it's a growth rate, or decay rate. Okay, but again, decay rate means we would be subtracting that. T is the time period. Now, you want to make sure that the time period always matches the growth rate. So in this case, we have 50% annually. So this time period is going to be in years. If it was daily, the exponent would be in days, etc. And y is our final value after exponential growth or decay has occurred. So looking at this new problem, right, we have a new computer for $2,100. That's an initial value. Okay, and it says the computer depreciated in value by 50%. Thing to remember, depreciate means to decrease in value. It goes down, it decays. Okay, so this one is going to be subtracted by the decay rate written as a decimal. So 50% as a decimal. Remember, you move the decimal over 2 places and we get 0.5. Okay, when will the computer have a value of 600? Well, it sounds like when is asking me to find the time for a final value of 600. Okay, so we need to solve this for t. How are we going to do it? Well, remember, we need to isolate our base by dividing out this initial value. So when we take 600 and divide by 2,100, we should get 2/7. And in the same step, I'm just going to, combine this. 1 minus 0.5 is actually 0.5 to the t. Now, to solve this, we're not going to get a 0.5 to look like 2/7, at least not easily. So what we have to do is we have to rewrite it as a log. So log base, my base is going to be this 0.5 value, right? Or the 1 minus 0.5 value of my answer is equal to my time. I plug that into my calculator. I get that 1.8 approximately is t. Now, what is the unit on that? Well, that's 1.8 years because this is annually. So let's take this as a larger question. So when will my computer be worth $600? Well, in a little under 2 years, it'll be over half the value. Less than half the value. So just keep that in mind. So what about this question? The foundation of your house has about 1,200 termites. The termites grow at a rate of about 2.4% per day. How long until the number of termite doubles? Well, this is a very similar question, except This time the termites are growing, so that's going to be a plus. And the growth rate is per day, so that means my time is in days. But other than that, we can still use y equals a1 plus r to the t. So what is my a, initial value? What's my r? Well, 2.4 is 1, 2. That's plus 0.024 raised to the t days. So now we want to know how long until it doubles. So what is 1,200 times 2? Well, that is 2,400, right? That's the doubling. So we're going to solve for t here. Divide by 1,200, which should make sense because this is 2 times. The base of this is 1.024 to the t. And all that's left is to rewrite this so that we can get our t value. So log base, this complicated base, of my answer 2 is equal to t. And what do I get? 29.23. And we are in days here. Okay, so we're